I'm Dr. Morsony. I'm a professor at Stan State in the physics department, and I'm an astronomer is my area of research. So today we're going to see a demo that you can do at home that's going to show us how to make a supernova. And so for this, you're going to need a basketball, and you're going to need a tennis ball. And I'm going to do the demo first, and then I'm going to explain how this relates to supernova. So what we're going to do is take the basketball, and if I hold it at my waist level here and let it bounce, let's see what happens. Okay, so it bounced about halfway up to my waist, about to my knees. Let's try it with the tennis ball. Hold it out about waist level, let it drop. Okay, it came up about to my knees as well. Now I'm going to try something different. I'm going to take the basketball, I'm going to put the tennis ball on top of it, and I'm going to drop both of them together. And what do you think is going to happen? Well, okay, you know the tennis ball is going to bounce, so it's going to come back up at least to my knees. Maybe since it's bouncing off the basketball, it's going to go up a little higher. Maybe it's going to come back to my waist. Maybe it's going to go up to my head. Maybe higher than that. Well, let's see. So if you're going to try this at home, be careful. Do it outside. If you can, wear some safety goggles or something. Don't let it come back and hit you in the face. Okay, let's see if we can do this. Well, that one went off sort of to the side. Let's try one more time. Tennis ball on top of my basketball. Let's see, good spot there. There we go. So that tennis ball bounced back to a lot higher than where it started. The exact same thing is going to happen inside of a supernova. If you have a really big star, something that's maybe 10 or more times the mass of the sun, when it gets old, it's going to start to contract because it's burned up all the fuel inside. It's burned hydrogen into helium, and then it burns helium into carbon, and then carbon into neon and oxygen, and so on, until you get a core that's made totally out of iron. And that core isn't producing any more energy. The iron won't burn. There's no nuclear reactions to get any energy out. So what happens is it gets bigger and bigger over time. Once it gets big enough, it collapses under its own gravity. It squishes down from something that's maybe several times the size of the Earth down to something about the size of San Francisco. And it makes a newborn neutron star. And everything that falls into that just stays there. But then you have the whole rest of the star around it. So that iron core is maybe a couple of times the mass of the Earth. A couple of times the mass of the sun. The stuff around it is still maybe 5, 10 times the mass of the sun. It all falls down onto it. And some of it is going to stay in that neutron star. It's going to get compressed or accreted as well. But a lot of it is going to come down. It's going to hit that newborn neutron star, and it's going to bounce off. And it's going to hit all the other material going out. And so you get this huge explosion. You change just a little bit of the gravitational energy of the star. Everything's falling down so far into outward momentum. And it destroys all the outer layers of the star. You get this huge explosion that makes a supernova. So same idea. You have a big mass and a small mass. That big mass isn't going to bounce very much, but the tennis ball, the small mass, is going to go shooting away. And there's our supernova.
So we've seen that if we have something collapse and then bounce, we can get this big rebound where it's coming out a lot faster than it went in. Same thing happens in a core collapse supernova. We have this iron core at the middle. It collapses under its own weight. The material above it starts coming in, and this whole collapse only takes about a second, and then the material bounces off the core. It sends a shock wave out that's going to destroy the star and make this big supernova explosion. The core actually collapses into a neutron star, so it gets so dense that protons and electrons get squeezed together and make neutrons. And when they do that, it releases neutrinos. These are very light, almost massless particles that interact only very weakly. but a few of them will get absorbed by the rest of the material in the star, and they actually boost that shock wave, and you need them to actually make the whole thing explode. So here is a simulation of a core collapse supernova happening. So that little blue circle in the middle is the newborn neutron star that's forming. It takes a little while. This is just a few milliseconds. Eventually, the material is going to start collapsing in, and then this is going to show the temperature of that material. So you start getting this incoming material getting compressed, and eventually it's going to start to bounce and expand, and you'll start to see a shock wave going out. And you're going to start to see hotter and hotter material as well. And this material, there'll be a bunch of nuclear burning happening, and you'll get different types of stuff getting made. You'll get like oxygen and iron and nickel, lots of heavy elements getting made in these explosions. And here, we're still at just about 150 milliseconds. So, much less than a second, we've got this big explosion moving out, and we've made different types of elements mixed in there. And the shock wave, it blows apart the remaining part of the star. The neutron star stays behind, but everything else gets blasted away. And a supernova has about the same energy as the sun is going to emit over its whole lifetime of 10 billion years. So this explosion has lots and lots of kinetic energy. They'll start to radiate over a few days, and then after a few days to weeks reach their peak brightness and then start to fade. And then they'll leave behind supernova remnants. This is the Crab Nebula. It's the remnant of a supernova that happened in the year 1054, so almost 1,000 years ago. But with telescopes, we can still see it, and we can see this really complex structure from this kind of instabilities created when this thing exploded. But the energy source is really the same as this tennis ball bouncing off of a basketball. Something's falling in and then rebounding and taking a lot of energy back out with it.